In this section, I want to analyze the issue of LightSquared attack on GPS and offer a solution. One thing that is good about the LightSquared saga is that it brings the issue of the in-band interference to the attention of many GNSS users, especially the surveyors and the high precision users. Being aware of the interference conditions before starting your survey job is similar to a pilot learning about the weather conditions before taking off. I strongly encourage you to view our two videos in this subject in javad.com website. One video is Introduction to GNSS Spectrum and explains fundamentals of in-band interference. The second video explains the spectrum analyzer feature of Triumph VS and shows real examples of interferences in cities and the effect of intentional jammers that are being freely marketed these days. Related to LightSquared attack, I want to touch on three issues. One is the issue of so-called collateral damages. Second is the issue of why high-precision receivers are affected more by the LightSquared attack. And finally, offer a solution. The first issue of collateral damages. The notion that is suggested by the LightSquared is that the high-precision users are about 5% of the total users. So, in the LightSquared attack on GPS, the damages to surveyors and to high-precision users should be considered as collateral damages and should be tolerated. If only the mere numbers of users are measure of significance, one can argue that military users should also be ignored because they are less than 1% of the total users. But when you add substance to numbers, you see how quickly the argument fails. Military is the backbone of our national security, as the high-precision users are the backbone of our financial security and growth. The next issue is why GPS high-precision receivers are more sensitive to any interference in general and to the LightSquared in particular. There are two reasons for this. Let me explain the first reason. This graph shows a general shape of a digital signal that represents ones and zeros of a digital signal. This is a clean signal. Logic 1 is represented by a clean high-level voltage, and logic 0 is represented by a clean low-level voltage. The second graph shows the same signal but slightly deformed by filtering and other effects. The next three graphs show the same signal increasingly damaged by interferences and increasingly deformed. In data communication applications, like in digital radios, TVs, mobile phones, internet, Wi-Fi, and all other applications that data is transmitted, there is no difference between the first clean signal on the top and the other four damaged versions below it. This is because the communication devices on the receiving end can recover the information bits as a 1 or as a 0 in all 5 cases in this graph. In contrast, in the GPS application and in all positioning applications, it is not enough to receive the ones and zeros correctly. It is extremely important that the shape of the signal to be as clean as possible, because in the receiver we use the signal to measure the distance to the satellites by looking at the arrival time of the edges of the signals. If the edges of the signal is disturbed, the receive time is fuzzy. To put this in perspective, note that the total width of a GPS L1 chip is about 1 microsecond. In converting time to distance, this means the width of a GPS L1 chip is about 300 meters. The width of the Pico chips are 10 times better, but still about 30 meters. In high precision applications, our main source of error is multipath. The distance between the direct signal and the reflected signal from the earth below the antenna is about 2 meters. We need to distinguish between these two signals. This is not possible if signal edges are not clean. A LightSquared engineer has suggested that GPS users should use narrow filters to reduce the effect of LightSquared Attack. Apparently, he does not know that if we use narrow filters, the shape of the signals will get affected and the edges of the signals will get rounded and the arrival time of signal becomes fuzzy. We already have extensive filtering in all of our receivers to protect GPS against out-of-band interferences. We use about 15 filters in each receiver. In short, we need to use filters as wide as the broadcast GPS signal, which is about 24 megahertz wide. Of course, we use carrier phase too, but the same principle exists for the shape of the carrier signal too. This is one of the reasons that high precision receivers get affected more. The second reason that high precision users of GPS are more affected by interferences are the fault of our US government, who intentionally, but without any good reason, has robbed high precision users from the full power of the Pico signals of GPS. High precision receivers go through much technical pain to use the encrypted P codes of L1 and L2 bands. Without going into technical detail, let me just summarize that the effect of the encryption of P codes is about 1,000 times degradation of the P code signal's effectiveness. The P code encryption is done under the name of national security. Our government some years ago was doing similar damage to the L1CA signal by intentionally degrading its precision. That was also done under the name of national security. After long arguments with GPS officials, they finally recognized that CA code degradation was not doing any good to anybody. And finally, around the year 2000, they stopped damaging the CA code signal. Archives of the GPS World magazine carry the history of our campaigns and advertisements. It is time for us to speak out and show that encrypting the P codes does not do any good to anybody. GPS officials are aware of this problem and they plan to add a non-encrypted signal to L2. But it takes about 10 years for this plan to become really fruitful. Russian GLONASS P code signals are not encrypted. Today, reliable and fast RTK is not possible without combining GPS and GLONASS. And last, I want to offer a solution for the LightSquared project. We love LightSquared. Communication is an integral part of GPS high precision applications. We love to use LightSquared channels to transmit corrections from our base stations and from our VRS networks to our rovers. LightSquared is a nice complement to GPS and to GNSS, provided that it does not affect base and rovers' range measurements. I like to offer my solutions in two parts. Part 1 is for the LightSquared to stay a bit further from the GPS band, as they have indicated a plan to do so, and for the LightSquared to use cascade of filters to reduce their out-of-band transmission as much as possible. The second part is for President Obama. P-codes should not be encrypted, at least until the new clean non-encrypted L2 signals are implemented in all satellites. Even if encryption is necessary, it should happen only on extremely rare cases when needed, and in rare locations where needed. I'm aware of some minor side effects and ready to discuss and offer solutions. For now, let us focus on this point, that not encrypting the P-codes make GPS less vulnerable to the LightSquared project. This will help us all to benefit from the LightSquared project while keeping the GPS high precision applications alive. One of my heroes is President Reagan. He stood in front of the Berlin Wall and said,
"Mr. Gorbachev, tear down this wall."
Let us all follow President Reagan and shout together, President Obama, end the P-code encryption.
Mr. Gorbachev, tear down this wall.